All right. Sounds like you can all hear me. So I wanted to say first, thank you to the organizers for putting on a great conference and also for the invitation to present today. And I'll be discussing the ice giant Dynamos. And the ice giants are kind of a colloquial name for Uranus and Neptune. So the talk will be broken into 4 parts. The first is just going to be an introduction to these 2 planets. And then they have some really unique features about them, and I'm going to focus on their non-dipole-dominated magnetic fields. And then kind of in the spirit of the similarities and differences between planets and stars, I wanted to do a short summary of some recent work that we're doing looking at magnetic fields and differential rotations dependence on the magnetic Prandtl number. And then conclude with looking ahead, including a description of the Uranus orbiter and probe mission that Dave just mentioned. So the first part is going to focus largely on the outstanding science questions that were identified by the recent Planetary Science and Astrobiology Decadal Survey that was released a few months ago, that was organized by the National Academies and gave recommendations to NASA and NSF. That's supposed to represent the broader consensus of the community. So in particular, I'm going to draw from chapter 10 of this document that is on giant planet structure and evolution. So one of the first questions is, what are Uranus and Neptune made out of? Which seems maybe like a silly question, but we don't actually know very much about their interiors. And I want to kind of illustrate that with this nice schematic where you have this outermost layer of molecular hydrogen and helium and ices, so they have your elements. You have most likely a water layer below that has potentially things like rocks that are mixed in there. You could have higher other elements like ammonia or methane. And then below that, potentially a central rocky core that may have ice in there as well. So besides the composition, there's a big question about how the mass and the different compositions are distributed with radius in these planets. So the traditional viewpoint is that you have these 3-layer models. So you have this outer gaseous envelope, you have this water ocean, and you have a central rocky core. But that has come into questions for about the last 10 years, where you instead have a more continuous distribution of these materials. So you don't have these sharp gradients in between any of these 3 different layers. So you could have these kind of more smooth continuities between these. So that's kind of the second question of how does this composition change with depth? So another aspect that relates to their interiors and also this idea of how both heat and materials are transported between the deep interior and the atmosphere is the energy balance of both of these planets. So there's some really interesting things about Uranus and Neptune compared to Jupiter and Saturn, where Uranus emits the least amount of heat relative to insolation compared to all the giant planets, and Neptune emits the most. So that's kind of reflected here. So Uranus only emits a little bit more heat, and potentially even none compared to amount that it receives from the sun. But Neptune emits more than 2 times what it receives from the sun. So that indicates that there's a different type of energy balance going on between these 2 planets, and Jupiter and Saturn kind of fall in between these 2 scenarios. So the explanation for this isn't really well understood. There's some suggestions or hypotheses for that. They include layers of stable stratification in the interior. They could either be thermal boundary layers, they could be compositional gradients, or they could even be potentially an atmospheric phenomena where this could be due to waves and time variable activity in the atmosphere. So there's a lot of unknowns about how the energy balance of these bodies are. So in related to this energy balance, if these differences in heat flow is related to the interior, then you have kind of 2 scenarios that could happen. And this is going to focus on Uranus as an example. In one case, you could have a very hot interior of Uranus. So if you basically trap all of your heat within the planet, then you're going to get a very hot interior, and then you could even have things like plasma in the deep interior. On the other hand, if you instead have a more icy Uranus scenario, you would instead have a much cooler interior, and then you can instead have phases like superionic ices that'll come into play in a little bit. So you can see that there's a lot of difference between these two pictures. And this is just one example of what these internal structures and compositions could look like. And there are many other models and possibilities that have been proposed as well. So kind of relating to the composition and the heat flow and the overall general dynamics, that kind of brings us to their magnetic fields. So what I wanted to just show here is a comparison of the gas giants, Jupiter and Saturn, that Jeremy nicely discussed earlier in the week. And you can see that they have more small scale structure at Jupiter and is very axisymmetric at Saturn. And if you look at Uranus and Neptune, you have a field that is not dipole dominated any longer. So you have these much smaller scale, excuse me, much smaller scale fields that you can just look at in these images. And then on the other side, we have the magnetic power spectra here just up to the spherical harmonic degree and up 3. And that just kind of shows it more quantitatively, where you can have the quadrupole and octupole components of Uranus and Neptune be comparable to or even larger than the dipole component, in contrast to Jupiter, Saturn, and the Earth, where you instead have this strong dominance of the dipole. The other element you can look at is the order. So if you look at Jupiter, Saturn, and the Earth, they're dominated by the axisymmetric component. But for Uranus and Neptune, you have, again, a different type of behavior where you actually have a peak in the m=1 equatorial mode, but you still have quite a lot of power across the spectra. So the outstanding question is, why do Uranus and Neptune have fields that behave like this, and why are they different compared to Jupiter and Saturn? So kind of the next question relating to the dynamics is, what is the deep dynamical state of the giant planets? So I'm going to kind of take this from the top-down approach. So if you look at the back images here, these are just the visual images of what the winds look like. And then superimposed, you have the zonal flow, zonal wind patterns superimposed. So you can see that Jupiter and Saturn have this large prograde jet at low latitudes, and you have these alternating bands of winds at high latitudes. And if you look at Uranus and Neptune, you have a really radically different picture. So here, you instead have a retrograde equatorial jet, and you have prograde jets at high latitudes for both Uranus and Neptune. So that's just what we see at the surface. And from the recent Juno and Cassini grand finale missions, we're able to get a lot of constraints about how deep those zonal flows might extend into the interior of Jupiter and Saturn. So on Jupiter, it's thought that these zonal flows extend into the interior about 3,000 kilometers. And then on Saturn, it's thought that they extend in about 8,000 kilometers. So similar type of analyses have been done for Uranus and Neptune using the Voyager 2 data, which I'll mention we just have one flyby that was done in the 1980s. So we have really limited data on that, but those analyses suggested that these zonal flows don't extend all that far into the planets and would be confined to a layer that's less than 1,000 kilometers. So that's just kind of the best estimate that we have so far about how deep these winds flow into it. But that comes into play because you might think about if they're this continuous distribution of materials within the interiors of Uranus and Neptune, you might have a coupling between the zonal flows and the dynamo region. So that's kind of a high-level picture of some of the things that we know and don't know about Uranus and Neptune. So next I want to just kind of go over a brief review of different proposed explanations for Uranus and Neptune's kind of anomalous magnetic fields. And this is going to follow a review paper that Sabina Stanley and I wrote a couple years ago. So there's, of course, a lot of different ideas that have been put forward, but I'm just going to focus on a few of them. The first is the one from Sabina and Jeremy from 2004 and 2006. And this was a really novel idea that if you have this dynamo occurring in a thin region that is overlying the region of stable stratification, then this could be a mechanism to generate non-dipole-dominated, non-axisymmetric magnetic fields. And this was motivated by the low heat flow problem that we talked about for Uranus, where if you have this layer of deep stable stratification, that might have been an explanation for why Uranus's heat flow is so low. So what they did is they have a series of numerical models that they run. So in this light blue area is the convecting region, and they have some models with a solid inner core. So that's what this red is going to indicate. And then a second set, they have an additional region here where it is fluid, but it's stably stratified. And then it again has a small inner core. So you kind of look at two different geometries. You can vary how thick each of these regions are. So the first results that I'm going to show are the cases where you have this deep, stable stratified layer. And these chi-s are going to indicate where the distinction between those two zones is. So in this first case, it happens relatively deep into the planet, and then it kind of goes up in each of these cases. So what you can notice is that in all of these cases, except for when this layer is quite thick, and you only have a relatively thin convecting region, you get non-dipole dominated magnetic fields in these scenarios. And then we can do a similar analysis where they instead looked at cases with a solid inner core. And now this is just going to change the geometry of the inner core. So this is the Earth-like geometry, and then you get thinner and thinner convecting regions as you get to these larger chi values. And what you can see is that you generally get more dipole-dominated solutions, with the one case here, and this case is unique because it has a different electrical conductivity in the solid inner core than in the conducting fluid region. So that kind of indicates that you need to have a solid inner core that is less electrically conducting than the overlying fluid in order to get this non-dipole dominated magnetic field in this suite of dynamo models. So then we can look at this a little bit more quantitatively, again, using the magnetic power spectra. So to just orient you here, this is going to be the power over degree. The Earth is given for context in these black lines. Uranus is in these boxes, and then Neptune are in these diamonds. And you can see in the cases with the stably stratified shell, the majority of cases do have this non-dipole dominated solution. And then they also are often able to get this peak at m=1 mode, which is quite encouraging. So you can do the same type of analyses for the models with solid inner cores. And again, as we kind of mentioned, that the only case where they found the power to not be dominated by the dipole was in this case where the inner core was less electrically conducting. But one other aspect when you look at the spherical harmonic order is that those models don't represent this m=1 peak that Uranus and Neptune have. And I should also mention that these observations are taken at one snapshot in time, and the spectral profiles from the models are taken in time average, and there is quite a bit of temporal variability. So you would potentially be able to find a snapshot in time that did match, and that's true for all of the models so far.
You're saying none of the models match that?
Well, for these models, yeah. With a little bit of a caveat that we just have one snapshot in time for the planets. So, yeah. Okay, so in recent years, there has been quite a lot of advances in material physics. And one of the things that they've been able to do is understand the properties of superionic ices. So remember at the beginning of the talk, I showed that there was a possibility of superionic ice in the interiors of Uranus, but also potentially Neptune. And one of the important things of that is that superionic ice has been shown to behave like a solid. So it's kind of illustrated here in this movie. So these blue dots are going to be oxygen molecules, and then these white dots are going to be protons that kind of are able to move freely through this lattice of oxygen. So it behaves more like a solid than a liquid. And additional work has shown that when you have this superionic ice, it also affects the electrical conductivity of those materials. So this is a plot showing electrical conductivity as a function of temperature. And the black colors are for the ionic phase. So that's when it is still a liquid. And then these blue colors are when you have the high pressure superionic ice phase. So what you can see happens is you have a jump in electrical conductivity from when you have this ionic water as opposed to the superionic water. And that has implications for both of the potential mechanisms for generating non-dipole dominated fields, that were proposed. So in the first case, if you have a deep, stably stratified layer, that's complicated by this potential presence of superionic ice. Although this is just for water, and we don't know how other materials that would be incorporated in the interiors would affect those properties. Okay, so a second approach that is some work that I've done a number of years ago would be to, instead of the origin of multipolar magnetic fields being kind of related to the geometry, it's instead that the interiors might be less rotationally constrained by, the convection would be less rotationally constrained by rotation in Uranus and Neptune that compared to Jupiter and Saturn. So these are models that have really strong inertial effects. So I did that by considering basically two dynamo models, one that has a thick shell geometry and one that has a thin shell geometry. And then I wanted to be able to compare those to non-magnetic cases to see how strongly the magnetic field influenced the dynamics. So in the models that I ran, I'll first show you on the top the thick shell dynamo model results, and then the bottom is going to be the thin shell results. And on these panels, I'm showing them at the full spatial resolution of the magnetic field. And then in this case, I've filtered them to only include up to the octopole component. And I should mention too, that one thing that I have a different interpretation of these models is that I'm assuming that these are very simple models of the planetary interior that go from basically the bottom of the dynamo region up to the surface of the planet. So that basically is going to neglect any variations with density and electrical conductivity. So that's many assumptions about the molecular envelope that I have made to simplify the problem. And the reason that that is important is because if you look at the resulting zonal flows that result in these models, you notice that you get a retrograde equatorial jet far from the rotation axis, and you get a prograde equatorial jet or prograde jet at higher latitudes in this thick shell model. And then kind of associated with that, you get these overturning circulations that are associated with that jet. In the thin shell model, you have a stronger influence of the magnetic field. So you have a similar retrograde jet, but the high latitude jets are significantly damped and become retrograde at high latitudes. But the point is that the magnetic fields are non-dipole dominated, and you can get these zonal flows that are reminiscent of those at the surface, which kind of begs the question about the interior atmosphere coupling. So we can then do the comparison between the magnetic power spectra. So again, the diamond shapes are going to be Neptune. The squares are for Uranus. This time I've included some additional constraints from Herbert 2009 for Uranus. We're able to go a little bit further out into the power spectrum. And both of the dynamo models that I ran are able to generate these multipolar magnetic fields. But if you look at the spherical harmonic order, we are also not able to reproduce this larger m=1 peak that the observations have. So that is one complication with this model. And the other one, which I actually think is potentially more problematic, is that it's not clear that Uranus and Neptune would be in the regime where you have this kind of three-dimensional turbulent convection in the first place. The scaling laws in terms of understanding when you have this breakdown of, say, columnar convection and differential rotation and things are a really active area of research. So I think there's progress to be made in terms of understanding how feasible this is, but that is a challenge at the moment. So some other ideas that have been put forward for Uranus and Neptune kind of start with the kind of more pervasive idea that inertia is kind of a ubiquitous factor of the generation of non-dipole dominated magnetic fields. And it's been talked about already in this conference that if you have, say, a plot of your local Rossby number and dipolarity, which kind of measures how dipolar your magnetic field is, if you have large local Rossby numbers, you have non-dipole dominated magnetic fields. And this plot, it's significant to note that these are all Boson-esque models that are really kind of in the geodynamo configuration. But there have also been studies that have looked at this for inelastic models and for models with different core geometries. So they're kind of superimposed onto this plot here. So the filled data points are going to be cases that are with the radius ratio of 0.6, and the hollow ones are for 0.2. And as you kind of go from bluish to green to red to purple, they're going to be increasing in density stratification with the planets. So if you can look at this local Rossby number phenomena, you generally notice that you don't have dipole-dominated fields for large values, but you do have evidence of a bistability where you can have multipolar dynamos for models with low local Rossby numbers. So that's significant. And if you look at this trend, you also can identify that really strong density stratification can inhibit this generation of dipolar magnetic fields. And that has to do with the generation of concentration of convective motions in the outer part of the shell. So besides density stratification, you can also think about electrical conductivity stratification, which is relevant for the giant planets. So this is some additional work that has used inelastic dynamo models, and they instead look at, or additionally look at electrical conductivity variations with radius, and that's what's shown in this plot here. So it's electrical conductivity as a function of radius. So this the green color is going to have a small stratification, and then as you get down towards this like cyan color, you're going to have a large electrical conductivity stratification. And the thing to notice is, again, this is going to be the density stratification on the x-axis and the dipolarity on the y-axis. When you have very little density stratification, you can have this bistability between dipole-dominated and multipolar. And it's also worth noting that if you have high density stratification, the way to get dipole-dominated magnetic fields is to have large density stratifications. So that kind of comes into play for the generation of dipolar versus multipolar solutions. So with that foundation, we can look at what the interiors of Uranus and Neptune might look like. And this is some plots of the density as a function of radius for the range of possible internal structure models that are possible given the current constraints from the gravity data from the Voyager 2 mission. So you can see that there's quite a large spread of possible density structures within Uranus and Neptune. And if you take the interior to about 98% out of the way of the planet, the maximum number of density scale heights you have is about 5.2. And if you take the more optimistic case, then you would have about 2 density scale heights for Uranus in this case. And then this is just a blow up of some specific internal structure models rather than these more statistical cases here. And there's also been some work looking at the electrical conductivity stratification near the outermost part of the planets. And then here you can see basically that you have a pretty rapid decline of electrical conductivity with radius. So it seems that you likely have a stronger stratification electrical conductivity than you do with density for Uranus and Neptune. And that is kind of consistent with these results from the dynamo models, that if you have large electrical conductivity stratifications, then a small density stratification would be consistent with a multipolar magnetic field. So kind of the takeaway from this part is that we don't have like a really detailed view of the magnetic fields of Uranus and Neptune, especially after what we have seen from Jupiter and Saturn, but it already is really unique. And one of the really fascinating parts is it has no known axes of symmetry, which has been a challenge for numerical dynamo models. And even though there are current models that exist and I think have a lot of promise, they are not entirely self-consistent with what we know about their internal structures and their dynamics, but there's a lot of exciting directions forward to take to kind of remedy that. So I next briefly want to discuss some results that I hope will be of interest to the solar community and the stellar community. And I'll admit that that's not my area of expertise, so I'd really love to hear from y'all about that. So There's a paper a number of years ago that put forward the idea that the magnetic Prandtl number will differ between high mass and low mass stars, and that could have fundamental implications for their magnetic field generation. So that's what's kind of shown in this plot here, where low mass stars that have these convective envelopes would have magnetic Prandtls less than 1. But if you have high mass stars that have these convective cores, PM might be larger than 1. So what we've done is we've taken the thick shell dynamo model that I just presented for Neptune, which I should note is at a convective Rossby number of about 1. And I varied the magnetic Prandtl number from 0.25 to 10. And what we see is you might expect in terms of magnetic field strength, if you plot the magnetic Prandtl number and the Alsacer number, as PM decreases, the Alsacer number decreases as well. But if you look at the spectra, I think you see something really interesting, where the cases with high PM, which are these bluer colors, you have a really distinct increase in magnetic power as you go to smaller length scales. And at really low PMs, you get this really significant quadrupole component. And then conversely, the models with high PM have a notable peak at m equals 1, or minimum at axisymmetric component. And then they slowly kind of become more axisymmetric. And that is just represented in this plot in the upper corner. That I just wanted to use that to kind of point out that we have these different regimes. And those are kind of, we call the axial quadrupole regime. On the other extreme, you have strongly multipolar dynamos. And kind of in this middle part, you have an equatorial quadrupole component. And I'll get to these R's and P's on the next slide. So when we look at these numerical models, we also investigated their zonal flows. I don't have these in terms of differential rotation, but I think you can generally see that in this case, where you have the high magnetic Prandtl number cases, you have a prograde equatorial jet and retrograde jets at high latitudes, where if you have your low magnetic Prandtl number, then you have the retrograde equatorial jet and prograde high latitude jets. So if you want to kind of look at this as a function of depth, not just at the surface, the lowest magnetic Prandtl number case is here. So you can kind of see that this is extending across all radii, and you can't quite see the meridional circulations as clearly there, at least I can't. And then you can kind of see this really dramatic change to higher magnetic Prandtl numbers. And then that's just quantified here, where I'm plotting the amplitude of the zonal flow at the equator, and you can see this big jump across this regime between PM of 1 and PM of 2. So the main point that I wanted to kind of show with these models is that by only changing the electrical conductivity or the magnetic Prandtl number, you can fundamentally change the behavior of the magnetic field, and then also the large scale dynamics, in particular the zonal flows, but it also affects the pattern of convective heat transfer as well. And then I just wanted to conclude with a brief description of the Uranus orbiter and probe. And this is the highest recommended new large scale mission concept that was recommended by the decadal survey to NASA. So this is like a real opportunity for system-wide science at Uranus and Neptune. So it has kind of connections across many different scientific disciplines. And that was one of the biggest, I think, reasons for excitement that was really broad across the planetary science community. So it's able to tell information about how the planets formed, how they migrate across the solar system, what they're composed of. It has a lot of tools to be able to understand the processes, and of interest to us is the interiors, how it links to the atmosphere, how the magnetosphere will then couple into the dynamo, and just kind of many physical processes. Uranus has 5 major moons that are really fascinating in their own right. So they're going to be able to determine if any of these have subsurface oceans and what the implications are for those potentially being habitable. And Uranus and Neptune are also really good analogs for exoplanets. So that's all discussed on a following slide. And then also, since we're traveling so far to get out to Uranus and Neptune, it's an opportunity to get involved with the heliophysics community, as well as you're able to sample like the solar wind and things as it traverses. So some basic things about the mission. So it would basically be composed of an orbiting spacecraft that would have a magnetometer, it would have a couple of imaging cameras, thermal infrared, visible near infrared, a bunch of spectrometers, particles and fields, and then radio science with USO. There will also be a probe that will detach and then be sent into the planet, and that will measure the atmospheric structure. It's going to be able to get the composition in terms of noble gases and different isotopic ratios and different types of measurements like that. So the timeline for such a mission, the primary launch opportunity that was recommended would be to launch in 2031 with a time of flight of about 13.5 years. So that would mean that it would arrive in the Uranus system in about 2045. There's a second launch opportunity the next year, and that would arrive at about a similar time. But one of the things that was really exciting about this mission concept is that there's opportunities to launch every single year. So we could still be able to get to Uranus, even if there's some type of delay in something. And the offset would primarily be the amount of mass that you could take with you. So it could have some influence on the science, but you would still be able to operate. So I'm excited for this mission. The last thing I wanted to mention, I kind of hinted at before, would be in terms of exoplanets. So there are exoplanets being detected all of the time. So earlier in the week, I went through the exoplanets catalog and got the latest numbers for types of exoplanets that have been detected. So the largest number of exoplanets are actually Neptune-like, which is why I kind of argued that Uranus and Neptune are really great analogs in order to understand exoplanets. And then there's kind of similar numbers of gas giants and super Earths with, I think they'll be increasing this box before too long. So in addition to detecting all of these exoplanets, there's also been advances in being able to detect magnetic fields for exoplanets. There's been theoretical work that have made suggestions for what the potential amplitudes might be. And there's some new studies that have been actually been able to estimate what the magnetic field strength is. I think they're for hot Jupiters, but that's still a great step forward. And that's, I think, an area of investment that the community, the funding agencies are interested in pursuing. So we might be able to actually get some information about the magnetic fields, hopefully, of these ice giant-like planets. And then if we're able to get these information about the magnetic fields and potentially get some information about how they rotate in terms of like prograde or retrograde equatorial jets, which I'm not entirely sure if that's possible, but if it could, then that could also really help test some of these ideas in terms of how the magnetic fields are generated within our own solar system. So I think that's another really powerful avenue that we can use in terms of comparative planetology to further test dynamo hypotheses. And with that, I will take questions.
Questions back there?
So your idea that convection, might be playing less of a role in ice giant dynamos, did I get that right? And that might explain their multipolarity. So but my question, first of all, did I get that right? Not backwards?
Oh, I wouldn't say it's convection is less
rotation.
of a rotation.
Sorry, I misspoke. I meant rotation, sorry. So does that correspond to some physical difference in your assumptions about the interior? Or is it not that simple?
I would argue it's not quite that simple. I had tried to get a little bit of estimates of where Uranus and Neptune and Jupiter and Saturn would fall in terms of like a local Rossby number, for example, to see if that kind of fits into the relative influence of rotation. And have results, but I'm not confident in them enough yet to make sure I didn't have a bug in my code. But we're hopefully be able to kind of get some estimate of where they fall on those lines. But it's not like a linear, one goes up, because there's enough different components of the interior that couple in together that I think you can't just do like a linear mapping or anything, unfortunately.
Thank you, Krista. You flashed by quite quickly, but there was a picture about the electrical conductivity of these ice giants, which bothered me quite a bit, actually.
Okay.
Because, yeah, that figure only goes up to 10 to the 3 Siemens per meter, isn't it? Yeah, in the right in the middle.
Yeah.
That's
Oh, I should point out too that
that's
this is
1,000
only.
times.
Yes, I should point it out. This is only the 0.85.
Okay, right.
Yes,
It's not the
thank
full
you.
radius, yeah.
Yes.
But even so, at 10 to the 3, that's 1,000 times smaller than the electrical conductivity of the Earth. And okay, these things are bigger, but they're only 10 times bigger. So the RM is 100 times smaller. And well, that is tiny. I mean, that's really hard to get a dynamo at all. I mean, we're talking about RM, the large scale RM of about 10. So
well, or you could have, I've kind of viewed this as a way, if you have, relatively low electrical conductivity, you are kind of fixed in terms of what your geometry could be. You need to have a critical magnetic Reynolds number. That suggests that your velocities are really quite fast. I mean, very, very simply.
Yeah, I mean,
Too simply.
Could be, I suppose, that the velocities are hugely bigger than but the heat flux is tiny. I mean, it's really hard to understand. I mean, what I'm really getting is can we really believe those electrical conductivities, or is this just a lack of understanding of the basic physics of what's producing the electrical conductivity in those bodies?
Yeah. These are numbers, of course, that except when you get down to 0.85, are not likely to support a dynamo by themselves. But the deeper region can.
Right.
And this region can certainly affect the flow.
Right.
Just as we think it. So in the case of Jupiter and Saturn, I would argue that it's 1 Siemens per meter that's of relevance. You have to remember Uranus and Neptune have strong winds. Now, of course, we don't know how they decline with that. Although there are constraints, which I don't think you mentioned, that come from looking at J4, sort of thing that Yohai Caspi and Ravita Led have done.
Yeah, the
That's
results.
one of the reasons why it would be good to have more gravity data, actually.
Right.
To understand the winds.
Right.
Because we don't really know what the winds are doing at depth. But I mean, the other comment I would make about this kind of graph is I don't think we do it. That is, I don't think we know enough about how composition varies with that.
This does make
actually do this with any kind of
assumptions about composition. So these ones are primarily hydrogen, and then the kind of variation comes in from the amount of water that's present. Yeah.
Water, by the way, I mean, it's well known that if you take pure, this is not pure water, but it's well known if you take pure water, you start to mobilize the protons when you squeeze it at a high temperature, and so you can get a dramatic increase. Even with
the super ionic.
And the stuff that dissolves in the water. So that's why, salty water, which is still mostly water, you can't support a dynamo with salty water, but it's a high enough connectivity that it becomes interesting. Anyway.
Yeah, I mean, I worked a little bit with Ronald Redman's group, Martin French, and so forth on these conductivities, and I remember there were higher estimates that so directed at the superionic phase, for example, to get at the conductivity, and then I used all these scaling laws with the heat flux, and I came up with RM 100 or larger, but it's not terribly large. But these are just very rough estimates. I think these curves will probably be revised in the future.
Yeah, they're still working on it.
I'm not sure whether the original claim is correct, but the original claim, which comes from Bill Nellis's work, based on shockwave data for what he called synthetic Uranus, is that the conductivity that's relevant for the dynamos in these bodies is actually coming from a mixture of water, ammonia, and methane, and it's protonic, which is difficult, but possible, given the uncertainties of what's needed for a dynamo. And that's where you get numbers up sort of 100 to 1,000 or maybe a bit more, and maybe that's enough, but we don't really know. And just to add to that, though, there are other things there. I mean, you can actually dissolve rock
Yeah.
in water at high temperature. We know that. And rock is iron. And you're probably still talking about using ions, not electrons, but there's even the possibility of a little bit of electronic stuff, which, by the way, is what we think happens in Jupiter and Saturn. Even though there's this huge band gap, the temperature's high enough that a small number of electrons get excited, and the conductivity starts to be interesting.
I had actually a question, Krista,
Sure.
concerning observations from Earth or with James Webb of Uranus, for example. I know that aurora observations help to constrain the magnetic field in the past. Are there plans for that?
With JWST, I don't know if you'll be able to get information about the aurora, because I think that was in UV wavelengths. And I thought
don't
James
remember.
Webb was predominantly infrared, but that's outside of my area of confidence. But I see one shaking head, yes, so that's good.
Way at the back, but you need to, well, hold on, I'll take it. Don't want to discourage people way at the back, although, of course, if you want to ask a question, you should sit near the front.
Thank you. Sorry about that. So nice talk, very nice talks. About a third of the way through, you showed a plot of degree of dipolarity against the Rossby number. I think with and without, that's it.
This one?
So looking at the plot on the top right, you've got some very dipolar ones and some which are not at all dipolar. Can you say something about the morphology of the velocity field in those cases? Is it sort of columnar for the top ones and pancake-like for the bottom ones?
I can't, Johannes or Uli, I think this was some of your work. Maybe you could comment on that. Do you know?
Well, my gut feeling is there's not a big change in the structure of the flow between the dipolar and the multipolar. Yeah, certainly there's some. There's not much.
Okay, so that.
I mean, it could be that, I mean, the one problem is in these simulations, you have strong zonal winds, and they don't like to go with the dipole here. So you have this high stability. You either have strong zone winds and not dipolar magnetic fields, so multipolar, or you have weak zonal winds and the dipolar strong magnetic field. These are two branches of solutions you find.
But the flow looks the same in both cases.
What?
No?
No. What is the same for cases?
The flow, morphology of the flow.
But the smaller scale convection one. I think maybe to comment on that, it's really due to the zonal flow, which is associated with the stress-free boundary conditions, not so much the stratification. In fact, in this model, Martin Schreiner got the same thing. It's just stress-free boundary conditions, and so the flow is different, as Johannes explained, due to the fact that the zonal flow goes crazy with stress.
Another question from anyone?
Thank you very much. Thank you for this nice talk, Krista. I have a question more about the model actually that you use in your anelastic simulation, because Chris Jones is probably more an expert than me about this subject, but different anelastic approximations exist. And are you sure that the anelastic approximation as presented by Chris 2011 is really the most suited for the Uranus and Neptune models? Because in this case, dynamo action takes place in a liquid actually, and it's completely different, I think, for Jupiter and Saturn, in which and for stellar interiors also, yeah, in this case, you have a gaze. So I think it's you can't consider exactly the same anelastic approximation for the different planetary interiors.
Yes, so the models that I showed for both Sabina's 2004 work and my work from 2013 are all Boosanesque. And then the ones that I showed for the changing PM affecting the zonal flows, those were all also Boosanesque as well. So the anelastic models I think that you're probably referring to are these ones.
Yeah.
And I think these were more oriented towards the giant planet, or motivated by the gas giants. And in terms of how that would affect Uranus and Neptune profiles in terms of anelasticity, I suspect that similar trends would emerge. But I haven't looked into that. Yeah.
Thank you.
Okay, thank you, Krista. Let's break for lunch and we will start up again promptly at 13:45. So.
Yeah.